So that's why the variance is important. So we have mean deviation. So mean deviation and all you can calculate like in an Excel also you can calculate the mean deviation. When we subtract the value of a column from the mean, it gives you something called a mean deviation. Then we have standard deviation. So let's calculate one of the standard deviation, because standard deviation generally I give in the exam for calculation. So I'm just showing you it using an Excel. So just give me a second. The Excel is not opening. Yeah, open. Okay, so let's copy some data here and let's calculate this variance. So let's calculate the variance and standard deviation. So in the exams, when we're doing calculation, theoretically, you will not get more than maybe 7, 8 values or 10. Okay, which you can do later. I just show you how to do this. Okay, so for example, let's take this total bill and I'm copying just 10 values here. So I'm just going to calculate the variance. Okay. So let's take total bill and let's compare the variance of this both. So this, okay, copying this. So total bill and these two values I copied. Okay, now I'm going to calculate the variance. Now, how do you calculate the variance? So we have something called deviation from the mean. So which I'm calculating, which is calculated by subtracting the mean, subtracting the total bill from the mean. So here mean minus total bill, mean minus total bill will give you the deviation from the mean. Mean minus total bill will give you the deviation from the mean. How do you calculate that? You can just calculate with by first you calculate the mean of this column. So mean is the average. It's the average here. And so this is the average. And here I am just subtracting this from the average. Okay, so this will give me the mean deviation. Now, as you can see, will be lesser than mean. Some of the values will be greater than the mean. So that all contributes to the mean deviation. That means some values are less than the mean. Some values will be greater than the mean. And I'm just copying this data here. So these are the values. Some values you can see they are bigger than the mean. Some values are lesser than the mean. So they are looking at minus. Just format this cell just for this. Okay, so this is the value. Now what I'm going to do, this mean deviation, now the deviation from the mean, now if you want to add them up and calculate a total sum, what will happen? The minus will cancel the plus. That means positives will cancel the negatives. Because of that, to prevent that, what we are doing, we are creating a column called deviation, mean deviation, deviation from mean square, deviation from mean and square. Deviation from mean square, and I'm writing equal to, so we have done deviation from mean square. After that, what we are doing here, we want to take out the average deviation here. Average deviation. The average deviation, this is called variance. We get a thing called metric called variance here. So which is the average deviation from the mean. So we take out the average. Average means we just take out the sum divided by the total number of elements. So if you are doing it in hand, so you are just doing sum divided by the total number of elements. So this is the average deviation. So the average deviation, this is called variance. Variance is the average deviation from the mean. Now, what is standard deviation? Okay, standard deviation is the square root of the variance. Okay, standard deviation is the square root of the variance. So I am just doing a square root equal to SQRT. So see the process. This is how we have to calculate variance and standard. So 6.306 is the standard deviation here. So this is standard deviation. Standard deviation, which is the square root of variance. Square root of variance. Now, if you want to check that whether it is correct or not, equal to STT. I think you have the standard deviation here. You can calculate the standard deviation of the column. So this is the column, the standard deviation you have to take out. Almost it is same. Okay, so there are a lot of standard deviation population means, so depending on the whether you are taking here, there are two types of mean which are taken. One is called a population mean, which I have done, like you take the total data divided by n. Then another is a sampled mean. Sample means total data divided by n minus 1. So that's why it's little bit different, like 0.3 differences there, but otherwise it's almost the same. So this is the machine calculated standard deviation. Okay, so here, have you understood this variance? This is called variance. Now you can check the variance. Now the standard deviation variance of this column is around total bill is 39.77 and standard deviation is 6.68. Now you can also calculate the standard deviation of this column. I think we have to calculate the standard deviation population. So this is 1.17 only. So now you can understand the variance, that means the variety of data which is in this total bill is much more than the variety of data that is in the tip. That's why the variance is much less here. So you can compare two columns on the basis of this. Is it clear? So we can compare, we can say that the variance of total bill column is much more than the variance of tip column. So total bill is a much more powerful column which is going to contribute a lot towards the prediction. Is it clear now? Any question you have? Are you able to hear? All right, you can directly take standard deviation here in Jupyter Notebook also. So I'm just creating here. Again, we are going to use, we can use a lot of, like for statistics, we generally use NumPy arrays because NumPy is for statistics. So for example, this array you can take here. So this total bill which we have created, we can just copy here, copying here, and I'm just doing import NumPy as NP. What is happening to this? Give me a second now. So I'm creating a new file here for today's date is 1209, right? I think I have added a video also in the classroom. Now I have added some column data. So here I'll just write NP dot, just see the syntax. If you're doing it, please do it with me. So this is NP dot array. See, we'll do NumPy also. We have that package, but right now we are doing it a little bit uh, before doing the syllabus because we need it for statistics. You can take the variables like this, for example. Now you can just do var, means variance x, which will give you the variance of x. Sorry, np dot var. So 39.77, we had also calculated it here. You can see it's exactly whatever we did, exactly same, 39.77. Then standard deviation was 6.3. So np dot std and 6.306. So you can see our value is absolutely matching here. You should know how to calculate the mean, you should know how to calculate the median, and you should know how to calculate the standard deviation. Do you have any, I mean, any doubts? You can ask. So generally, you should focus on the standard deviation only. The other deviations like quartile deviation, they are not so popular metrics. So standard deviation is the only very popular metrics. Okay, you can also talk about the range. Range means the maximum of the column minus the minimum of the column. So you can see here how we calculate standard deviation. So this is the data points, and we have the mean average of average is 5. That means we sum up this and we divide it by 8. That is the count of total number of elements. And after that, variance is the sum of squares of differences between all numbers and means. So here you can see 2 minus 5, because 5 is the mean here. So 2 minus 5 equal to minus 3, and then we do a square of 3. 4 minus 5 whole square equal to 1. 4 minus 5 whole square equal to 1. Like this, we are doing everything, and then we calculate variance, means add up every elements, divide by 8 equal to 4. That gives you the variance. The standard deviation is square root of variance. So we do a square root and we get the variance. Okay. All right. So we are doing the case study of Boston here. So Boston, we can calculate the range here for a Boston data set. So Boston data set, we can just import the Boston data set here. We calculate the range, then we can calculate the interquartile range, which is called the IQR, which is Q3 minus Q1. Okay. So we are going to do in Python. Here some code is given in the for the mean. Then average deviation from the mean. That means we just take out the deviation and take out the average. That is the average deviation from the mean. Okay. So average deviation is absolute value of xi minus x, mean of x. That means each value of the mean minus the each value of the data point minus mean value divided by n, and sum divided by n. But here we are, instead of doing a square, we are doing an absolute value. That is called mean deviation. So a relative measure of dispersion for comparing distribution of two or more data and unit free comparisons. The coefficient of quartile deviation also we have. It is formally defined as a coefficient of quartile division, which is Q3 minus Q1 divided by Q3 plus Q1 multiplied by 100, which is also a measure of dispersion. So, for example, you have this day and frequency, the number of vehicles sold by a major Toyota showroom in a day was recorded for 10 working days, and the data is like this. So 1 day frequency, number of vehicles is 20, 2 days 15. So you want to find the quartile deviation and coefficient for the given discrete distribution. So how do you find the quartile deviation? So you have to find Q3 minus Q1 divided by Q3 plus Q1. That will give you the quartile deviation. And you can calculate the mean deviation also. So we also have something. So here, basically, we can compare two lists. Okay, so that is the use of this variance. For example, you have two multiple choice questions. So you can compare them by calculating the standard deviation or calculating the quartile deviation, and compare that which multiple choice questions have more variations. Here you can see the randomized and answers have more variations. Okay. Next, we are talking about, so compare the two results, and comparing standard deviation doesn't really work, which means are different. Calculation of the formula, coefficient of variation, which is standard deviation by mean into 100, helps to make sense of the data. So here, what it is saying directly, if you can, we compare the standard deviation of two particular tests. So, for example, here regular test and randomized answer, and we can see that the randomized answers have a standard deviation of 12.7, which is little bit more than the standard deviation of regular test, which doesn't give you actually a clear picture. So, because standard deviation of two lists can we are comparing though, but they have nothing in similar, the means are completely different. So what we do here is we find the coefficient of variation. If you want to compare two lists, you should calculate the coefficient of variation, which is standard deviation by mean into 100. So that gives you coefficient of variation. So you can calculate the coefficient of variation. We just did like here for, I think we did the standard deviation, which check the standard deviation of two columns. One is for the total bill, another is for the tip, right? So you can calculate the tip also. See, whenever we calculated it on Excel, the standard deviation of the standard deviation of the bill shows 6.3, while the standard deviation of tip shows 1.17. Okay, so let's see what is the actual picture. So here, let me take the copy. I'll just copy the value here. Anyone is doing with me? Just write in the chat yes. Anyone is doing the practicals with me? Here I'm adding this y, and I want to compare the both the columns with the help of coefficient of variation. Standard deviation of this is the standard deviation of bill. The standard deviation of bill is 6.3, and the standard deviation of tip is 1.10. Let's calculate the coefficient of variation. So coefficient of variation, that is CV. CV of X is calculated by standard deviation, which is here np dot stdx divided by mean of X, np dot mean of X multiplied by 100. Okay, so which is giving given as, here just, okay. Now coefficient of variation of Y is equal to np dot standard deviation of Y divided by np dot mean of Y multiplied by 100. See, both are almost same. Actually, though it was looking that there is a drastic difference. it was looking as a drastic difference. It has 6.3 and it has 1.10, which is a drastic difference. That means bill has a lot of standard deviation. It has a lot of variance, that column, but tip does not have a lot of variance. But when you check, compare the means, you take the means into account, you see that actually tip has more variance than bill. Okay, so it is 39 and it is 32. So you can just infer that the tip column has more variance than the total bill column. That means the variance in the sense the values are more, has more variety. The values are more dispersion. Instead of variance, you can write dispersion. That means the values are more scattered. The values are more distant from the mean. Okay, so that is what we can analyze. So next we are talking about the shape. Okay, so there is a lot. Whenever you are doing analysis, there's a lot which you can find about the shape of the data. So specifically, so we do a lot of visualization here, and there are univariate analysis, there are bivariate analysis. Specifically, we are talking about the univariate analysis where skewness is a matrix which tells you the amount and direction of skew, and kurtosis tells you how sharp, tall and sharp the central peak is. So we are talking about distribution. That means when we measure the distribution of data in a particular column, okay, so the distribution curve we can measure like this. So when you plot the distribution curve, it looks like a bell. This is called a bell curve. So the bell curve, when the distribution is normal, the curve looks like a bell curve. But when the distribution is not normal, what is meant by normal? Normal means most of the data are actually centered, that means towards the mean. So most of the data are around the mean. So that is called normal distribution. In that case, the median of the data, median of the column is equal to the ideal situation mean of the column. The difference between mean or median is either zero or very low. Okay, so in that case, we call the data to be normally distributed. But in normal cases, there can be cases where that is not the situation, and we can, when we plot the curve, we can see scenarios like this where you can see the right tail is extended and the data is called skewed. So skewedness is a feature in which the mean of the column is becomes much greater than the median. Mean is greater than the median. And the right tail becomes longer and the data is called skewed. Okay, why that happens? So in a data, in a particular list, for example, if you have data like 10, for example, you're getting you're calculating the, you have a marks. Okay, so you have marks like, for example, 50.5, 80.6, 90.7. Okay, so if your marks are centered, like for example, it's 90% or 85%, and suddenly there is a fall like 40 or 30, something like that. So in that case, your data will become like this, and your left tail becomes longer because your mean falls. The median is here, but the mean falls here. because of the some data which is very trending low. Okay, so in that case, this is called the left skewed data. This distribution will show you how your data is placed. That means whether your data is normally distributed or your data has some of the data points are very low because of the low value. Because of that, the data has skewed to the left, or they are very high and they are skewed to the left. So in this happens only because of some exceptional values, and they are called outliers. So you can see this, just focus, don't focus on the code because this code is an R code. So you can see the how the distribution looks like, and there is a tail on the right hand side. So this is the MEDV, this is the distribution of the MEDV column of the Boston data set. And this data is right skewed. That means the mean is more than the median. And we have outliers. Now compare this data with this data. This data is more skewed, and you can see the tail is, you can't even see, it's so high. So when the we also have a matrix called kurtosis. So skewness and kurtosis, this two metrics. So kurtosis defines the how sharp your the this distribution will become. The more sharper the distribution becomes, that means more peak the distribution has, the more outliers it has. So it will, that means it has very heavy outliers. So this type of skewness is naturally more severe than this type of skewness. Okay, so this has less kurtosis, but this has more kurtosis. So we have these two metrics, skewness and kurtosis, to measure the shape of the data. You can see now the clearly the shape, how it is. And so this is for the Boston data set, and we are talking about the property price column. And this is the Boston data set, but it is for the crime column. So crime is always very, it has a lot of outliers because crime is very unpredictable. It is always an exception. If crime is not, is a pattern, then you can actually catch the crime. Because it's an exception, it is difficult to solve or difficult to prevent the crime. So importance of shape. One application is testing for normalities. Here, many statistic inferences require that the distribution. Okay, another thing is that here, whenever you are doing some machine algorithms or any kind of predictive analytics, now there is a there are some models required that the data has to be normally distributed. Data should not have outliers, because if you have outliers, then you are not able to detect the pattern. That means you are not able to understand the pattern of data, and in that case, it is difficult to understand, analyze the pattern of data. Okay, in that case, some of the models, that's why do not allow the data to be normally distributed. If you have normally distributed data, I mean, if you do not have normally distributed data, then the accuracy comes low. Okay, so the main validation of a model is that you should have normal distribution, then only you can do the model. So that is the testing for normality. Then we have skewness. Skewness is known as degree of distortion from the symmetric bell curve. So generally as I told you, if a data is normally distributed, the data will be like this, like a symmetric bell curve, and the mean will be equal to median. It measures the lack of symmetry in data distribution. It is unimodal, has just one peak, like most data sets. Next thing you notice whether it is symmetric or skewed on one side. So if the bulk of data is at the left and right tail is longer, we say that the distribution is skewed right. So you can see if your data is like this, so it is called skewed right. If your data is like this, it is called skewed left. So we have positive Q, we have symmetrical Q, we have negative Q like this. If skewness is zero, the data is symmetrical. If skewness is less than one or greater than one, the distribution is highly skewed. So here, how we measure skewness? So if the data is high, data is more than the skewness, calculation of skewness is more than one, then we call that the data is highly skewed. So you can see the for Boston dataset, the skewness of uh, MEDV column, which is the property price, is 1.10, which is highly skewed, but skewness of crime column is 5.2, which is very high. So if you do the outlier analysis of a skewed data, skewed column, you'll see that it has a, if you calculate the, print the box plot, you'll see that it has a lot of outliers. Similarly, we are talking about kurtosis, which talks about the tails of the distribution, not the peak. That means we are talking about, here in kurtosis, we talk about the, here, the peak. That means how much high it is going. It is used to describe the extreme values in one versus the other tail. It is actually the measure of outliers present in the distribution. So high kurtosis in a dataset is an indicator that data has heavy tails or outliers. If there is a high kurtosis, then we need to investigate why do we have so many outliers. So in case you are getting very high outliers, like I told you, the crime is a very, it's a alarming rate. The outliers are very high. It was showing like this. So outliers are very high. The skewness is showing as 5 point something. So in that case, it indicates a lot of things. It can be wrong data entry, or it can be an exception. It can be unpredictable situations and so on. Kurtosis in a data set is an indicator that data has light tails or lack of outliers. If we get low kurtosis, then we need to investigate the data set. So here, as per kurtosis, we have three types of kurtosis in your data. One is called leptokurtic, the second is called mesokurtic, and the third is called platykurtic. So leptokurtic is when your outliers are very high, like it is going high like this. Next, we have mesokurtic, and then we have platykurtic when we have little or no outliers. So mesokurtic, this distribution, kurtosis has a the skewness. I'm telling that the skewness is high when it is more than one. Kurtosis is high when it is more than three. So distribution has kurtosis statistics similar to that of normal distribution. It means that the extreme values of the distribution are similar to that of a normal distribution characteristic. The definition is used so that the standard normal distribution has a kurtosis of 3. Distribution is longer, tails are fatter. Platykurtic distribution is shorter, tails are thinner than normal distribution. So you can say this is the kurtosis. Kurtosis of property price is 4.46, while kurtosis of crime is 39.7. So with the help of this, we can actually do an outlier detection. Sometimes outlier indicate a mistake in data collection. Other times, though they can influence a data set, it is important to keep them better understand the big picture. So you can also sometimes whenever you're doing a model or you're doing some predictive analytics, it comes out upon us that with what kind of decision we can take. Do we want to drop outliers or not? So before that, we'll just do this in Python about the skewness. We'll check the skewness here. Yes, are you following? Do you have any question? How many students are doing practical with me? Can you just write here? Just write here your name. Yes, I'm doing. Just write yes. Okay. All right. So I'm going to do some visualization here now. So you can take the tips, this data, and let me see the visualization if it is giving me some significance. So data. So here you can just import the libraries here for visualization. To import, I'm just writing here visualization, visualizing the shape of data. Okay, now I'm going to do the univariate analysis. So what I'm doing a plot called distribution plot. So SNS dot this plot. I'm just using this X. Where is this X? You can see this. This shows a histogram, but I want to get visualization. So this is a very small data. So we'll write KDE, which is kernel density estimator. I want to choose. I've taken just a segment of the data, which is not actually showing me much. It's very small segment. Okay, so let's import a data. You can import this data called tips data, which I'm using here from the Kaggle, or it's available in GitHub also. Just download. See, we have pandas
Web,
data.
web.
Pardon? Yeah.
Hello, web.
Yes,
Web, can you bring? Can you
I
can
can't
you show
hear. Yes.
previous? Can you show the previous code?
Yes, yes. This one.
One. It's not visible.
It's not visible. Wait. I'll increase the size. Can you see it? Can you see now?
Screen is not shared, ma'am.
Yes, ma'am.
Screen is
Screen.
not. Okay. Before it was shared, no?
Yeah.
Yes, ma'am. Yes, ma'am.
Yeah. So what I'm doing here, instead of this is not showing me much the full graph. It is not showing because I have just taken a part of the data. Okay. So this I had taken the same X. Uh, okay, I can paste this data in here. But what I'm doing now here is getting the data from the mm, and data from the web. Okay, and because you anyways have the pandas, so before that we'll just do the statistics on the data. You can also take use this. This is why. Okay, so what I'm saying is go to your Google and just write tips.csv download like this. And you can have it is there in the Git also. Okay, why it is asking for my password? Download from Kaggle only. Download like this. You can download. I already have the data. You don't need to. I think here you if you download, you don't need to download as a zip. It will just get downloaded as a normal CSV file. So here. Okay, just download as a CSV file, then you will import here. So let me do some visualization and see the shape of the data. Generally, we do univariate analysis with this. So I'm just importing the data set here. I'm just sharing this link in the classroom. I mean, the meeting. Yes, okay. So here we have to import this pandas library. Okay, now I'll take out the distribution of this total bill. So SNS dot this plot.
Ma'am, can you show the code?
Yes, sure. Yeah.
Ma'am, the link which you have shared of the data set that we have to download.
Yes. Then how will you get this?
Okay, one.
Here, after you download, for example, whatever your wherever you're storing the link, like here I have stored in CSV you have to copy the path of this. If you copy the path, otherwise you copy the path from your address bar, whatever it is, and you write the path here. But whenever you're writing the path, you're copying the path from there. It is a Windows path, it will be having backslash. You have to write the path with the front slash because otherwise it will give you an error. Okay. And write this back in a Linux style with a front slash.
Ma'am,
Yeah.
I downloaded
Yes,
the file, but it's not coming.
it's not coming in the sense. Why?
It's not showing
Just show me. Show me your screen.
one.
Yeah, show the download. You have to go down, go to your Kaggle. Not this download. Don't click on that. Go down. Can you maximize your screen? I can't see properly. Can you maximize this screen? Yeah. Go down. So here there is another arrow. You'll see. Uh, there is another arrow in tips dataset. Tips CSV. Beside tips CSV, there is a. Okay, click on download. Let me show. That actually. Fine, you can do this also, but you have to zip. This is a zip file. See, I'm just showing you again. Stop sharing.
Okay.
Okay, great. Now here, see, here there is an arrow. Can you see? This arrow you click. You are clicking on this one. Here, if you click on here, you have to download the zip file.
Yes, ma'am. Click download it.
Uh, So if you downloaded it, then it is going to go to downloads, I suppose. Okay, like it is coming here. So do that. create a folder in C drive because we are going to work with more data files. And here, click on a folder called data or CSV and store the file over there. Copy the file here. Create a folder called data and copy the file over there. And then give the reference of this over here. 5 minutes, do that. After you've done, just
So first we have to copy the.
yeah, better don't copy the downloads. Otherwise, you can copy the downloads path also. But it is like it is going to be big path. If you copy this path also fine. Like right click here, downloads, copy as path if you have Windows 11, and then you copy this path over here. Just change the slash to front slash. Yeah. Okay, have you got it?
Yes.
Once you got it, so you can write this code. If you're done, just can you write uploaded in the can you write uploaded in the chat or imported? You write imported in the chat. We are writing df tip You can see this is how right skewed. Okay, so you can see the right tail is longer. If you you can this is a histogram basically, but you can print the KD also here. And if you want a KD plot, so this will show you distribution also. This one, so it shows the skewness. Okay, you can identify that this is right skewed. See the code. Histogram, and it shows that this is a continuous variable, continuous numeric variable, because there are no gaps in between. Okay, so you can just write this is right skewed. You able to do this? What about the diagram? What about the visualization? Could you do? So the distribution, so I'm writing the distribution plot shows that the data is right skewed. So right skewed is also called positively skewed. Okay. Shows that the data is right skewed. So right skewed means positively skewed. That means it will be positive. So you can actually calculate the right skewed here, whether it is skewness also you can calculate here. In p.skew and get the data like df tip, for example. Or you can write df tip.skew also. Just write df tip.skew will give you the skewness of this data. So you can see the skewness is beyond 1. I told you if it is beyond 1, so positively skewed data or right skewed data, and the beyond 1 means it is also called highly skewed. Okay, so this is what you can also calculate the kurtosis. Okay, so kurtosis is df kurtosis. I told you kurtosis should be 3. Okay, less than 3. If it is more than 3, it's called leptokurtic, and it is like kurtosis. That means it has a high degree of outliers. So kurtosis also you need to print here. This I'm not giving you to calculate manually. This is just for the practicals. Okay, so kurtosis, and it shows that, so skewness, it shows that high Wright's cube. And kurtosis shows that it is leptokurtic. Leptokurtic is the shape with heavy outliers. Yes. Have you done this? Just if you have done, just write done. So this one, and then we have done this. Write done in the chat box. Okay, done. So only 4 people, I think. Others, are you facing any issue? Yes. We did the outliers. We checked the kurtosis. Okay, now we want to, we are saying that it has heavy outliers. How to prove that it has heavy outliers? You can check a box plot. Okay, so I'm just calculating the box plot here. So box plot to prove of heavy outliers. So I'm using SNS or the Seaborn dot box plot. And here I'm printing the outliers TF tip. Does it show outliers here? Yes, it shows some of the outliers. Now, what is the yesterday last class we had calculated. We have learned that how to calculate outliers. So let's calculate the outliers of this column. Okay, this calculation of outliers also I generally give in the theory exam. Okay, so but you'll not get a very big list. It is maximum 6 to 7 elements will be there. So for calculating outliers manually, you have to arrange the list in sorting order, ascending order. After that, you have to find the median, and you divide the list into two lists, left list and right list. And from the left side also, you have to find the median, include the median which is there in the middle, and on the right hand side also you have to include the median. So you get q1, q2 and q3. Okay, after that you calculate the IQR, which is q3 minus q1, and then you calculate the upper bound, which is q3 plus 1.5 multiplied by IQR, and you calculate the lower bound, which is q1 minus 1.5 multiplied by IQR. Okay, so here to outlier calculation. So I'm just calculating the outlier. So Q1 here is NP dot quantile and df tip next. This is the Q1. Next, we are talking about Q2. NP dot quantile have Q3 NP dot quantile Okay, so these are the Q1, Q2, and Q3. These are the two types. Then we are calculating to find out the outliers. We have to find the lower bound and the upper bound. So we are finding the IQR, which is Q3 minus Q1, and upper bound is equal to 3 plus 1.5 multiplied by IQR is the upper bound, and the lower bound is minus 1.5 multiplied by IQR. This is the lower bound. Okay, now I will check that any data is there in this tips, in the tips column, which is basically more than, so there cannot be anything minus. So naturally there is no lower bound here, no outliers, but there can be data which is more than 5.9. So I'm just going to filter that data. Okay, so DF upper bound. So DF, and here you can write the filter option. Okay, so DF dot tip greater than UB. This will give you the data, which is the outliers. You can see these are the people who are outliers. I think how many numbers are there? Nine records are there who have given extremely high tip, around more than $7 or something, around $7. So which are considered to be outliers. And because of that, this data, this tip is actually getting skewed. Have you understood? Are you understanding this concept? Okay, do this. to the calculation. Once calculation is done, just write outlier calculation done. Okay, done. Done. Okay, yes. Good. Are you doing or you can check this. First, we have calculated the quantile. Okay, now what to do with this outlier? So there are many things which you can do. First is one is you can remove these outliers. Okay, remove these outliers from your data set. You don't need the outliers. So you want to it is causing skewness, so you can remove this outliers. The second thing you can do something called there is something called floating and capping. Okay, so floating and capping, what it does, please write here in the chat that it is done. I can see only Yash has written. None of the others have written that it is done. So can you just put it here if you have done this? Yeah, so if you want to drop or keep an outlier, so handling outliers, actually what we can do here, we can replace outliers with the value, with some value. So we can replace them with the mean, we can replace them with the median. If they are continuous numeric variable, we replace them with the mean or median. If it's a categorical variable, we can replace them with the mode. We can also do something called capping. So we have something called capping and floating. Capping means remove the replacing the outliers which are below the lower bound with 0.5 percentile of your data. And capping means replacing the outliers which are above the upper bound with 95 percentile of data. Okay, so this is called capping and floating. We also can perform a transformation which is called log transformation that also reduces the outlier. We have a package also which is called Box-Cox transformation or power transformation, with the help of which we can do a lot of transformation, like -2 here. It means that we are doing a square transformation. We also have square root transformation. Okay, we also have log transformation. So all these different types of transformations are there. So I'm just doing some basic handling of outliers. So handling of outliers. Let's do some basic handling of outliers. First is if you may want to remove the outliers, okay, from your data set. So I'm just writing df1 equal to and I'm checking I'm df and I'm just filtering this df with df dot tip not equal to or less than equal to ub. Okay, so that is going to remove my outliers because I'm removing, but the problem with this scenario is it is going to remove a lot of data from your data set. And another thing is when you're removing that outliers, it may be possible that you have new outliers because you are actually changing the mean. Okay, so let's see if I have removed the outliers actually or not. So df1, so I'm just doing a box plot of this df1. So SNS dot box plot And yeah, the outliers are almost removed. Okay, so it's better than the before because the data was like this. Now the data is like this. So it's much better. Okay, you can change the color. Okay. Okay, so the data is like this. So it is much better than the before. The outliers have changed. Okay, so I have created a box plot, right? See the code here. So first is I tried removing the outliers. This is removal of the outliers. So I'm removing. So this is done, right? Next technique which you see, I have not changed the actual data set. I have copied in a new data set. So the actual data set is still unchanged. So next, but this is the problem of this is you are going to remove a lot of data. So we are losing data. We are losing a lot of pattern. It's possible that that contains some information. Just for the tip, I am removing the other data also. You know, all the other records.
पण झाले
So,
म्हणजे ते एवढं हे नाही त्याला अजून 15 दिवस आहे
hello.
नाही होत नाही
Can you
होत
mute yourself?
बोल रिटर्न नाही होत आता मम्मी काय करणार त्यांनी नाही घातली तर म्हणायचं, तू नाही घातली तर कोणच नाही घालणार मग बोलायचं आपल्यासाठी त्यांचा मूड आता नाही हिच्यामुळेच झालंय मी सांगते ना
Yeah. Next technique which we doing is called capping. So capping basically means that I am replacing the outliers with 95 percentile of the data. Capping of the outliers. So here I calculate the 95 percentile of the data. So cap I am calculating. Cap equal to NP dot quantile. So this is the cap. So I'm going to replace the outliers with this cap. So what I'm doing here is df. See, we have not done pandas with you, but I'm writing pandas code. But pandas code is easy. It's not difficult. Okay. So are you understanding this one? Are you able to do? When we do pandas, that time we'll do more elaborately. So I'm just doing some code, not every code, but yeah. Are you understanding this code? Only commands. Okay. Because this does not have any code, Python programming or anything. Yeah. Okay. So Abanikanta, which one you are not understanding? Others? So here, see here, we are actually when we import the data here, because we have not done pandas. This part you understood, the standard deviation part.
Yes, yes. Yes. Yes, ma'am.
So here the pandas basically store the data in a table format, and it's called a data frame. Okay, so we read the table format, and this is called a data frame. So data frame has here we have columns. So columns are passed as an index. Suppose you want to print total bill, so you write this is a data frame. Data frame is like a table. So data frame and total bill. So like this. So this is will give you the data of that column, particular column. Okay. So if you want to check the first 5 columns, you can just write head. We are doing this plot, which is a visualization. This is called a distribution plot. Which is called a distribution plot. Okay. So and creating a histogram. Okay, distribution plot. So it will create a histogram. So we have to pass that column. It's called univariate analysis. So DF tip we are passing, and we are writing KD equal to true. We'll draw this line here. Okay, so it's called kernel density estimator. So this is going to draw this line. So here this is called a skewed distribution, because it shows you the histogram as well as the distribution of the data. Yes. So up till this you understood. So here in any column, if you want, you just write the name of the data frame which you have created. Like we have imported this data frame. So read.csv from pandas will read this data frame from the CSV file, and this is the location of the CSV file. Okay, so we just read it, import it, and each column, like if you want to print smoker, what you will write, df square bracket smoker. So we have more ways to access it, but we are going to do that during when we do pandas. So here, simple. So you are just using columns. I don't think more than that is required here. Okay, so these columns I want to calculate the skewness, so dot skew. This is a command. Then dot kurtosis. Okay, and for visualization, I'm using sns.boxplot, and I'm passing the column here. So yeah, it's a bit of practice. You can do this. Otherwise, you can see the demo, because there is no other way to explain statistics rather than this. Otherwise, you have to do the theory and calculation. So here we have done this, and the box plot will show you the outliers here. Okay, so outliers are showing that it is more than 6. The outliers, so clearly showing more than 6. So you can calculate all the outliers also. So I'll calculate outliers can be calculated with np.quantile command. This is there's no concept in it. You just have to remember. NP is NumPy. NumPy is numerical Python, a library of Python to do for doing statistics and numerical calculation. And here I'm passing the column which is df tip, which I just told you that any column has to be referred like this. Data frame is the name of the table which you have imported. And here I'm giving Q1, which means that it is 25 percentile of your data. Then we have Q2, which is the median, which is the 50 percentile of your data. And then Q3 is the 75 percentile of the data. And then we calculate the IQR, which is Q3 minus Q1. Upper bound is Q3 plus 1.5 multiplied by IQR. And lower bound is Q1 minus 1.5 multiplied by IQR.
IQR stands for what?
Interquartile range.
Okay.
Q3 minus Q1, it's called interquartile range. Okay. So here, so we calculate the upper bound and lower bound, and after that we see that lower bound is very low. That means we do not have to actually calculate any outliers towards the lower bound. So upper bound is here, it is showing as 5.9. So what we do, we want to handle the outliers. So we are filtering the data which is more than the upper bound. So here you can see I have passed that tip. You can write dot tip, or you can here also you can write like this. So also you can write. Okay, you can write it in both the notations. You can either write dot notation, or you can write square brackets. So here I am showing that DF tip is greater than UB upper bound, and it shows me the data. Okay, you can instead of writing DF bracket square bracket tip, you can also write DF dot tip. It gives you the same result. Okay, this also you can do. Okay. So both the notations are available, and yeah. So I showed you this. Next, yes. Next, I told you that I'm removing the outlier. So I have filtered the data which is less than the upper bound into another data frame called DF1. And here the data frame, and I check the outliers of the data frame, and I see that the outliers are almost removed. There is another technique of looking at the replacing the outliers, which is called capping. Okay. So here, so it's okay. We can give this practicals at the during when we are doing pandas. Okay, but then I'll give you some calculation to do during the statistics practicals. Instead of this, I will give you some calculation. That also is possible. If you are not able to do it,
Now,
or if you are able to do it, then yeah, pardon.
now understood. Most of it understood.
Understood, right? So these are just commands. There's no logic like that you have to know
We have
any
to remember
programming
the
concept. These are, yeah, you have to remember the commands. There's nothing, there's no programming concept involved like in core Python. Okay, so this is a library, and you have functions. So here, the cap I have found is the 0.95 percentile, and it gives me 5.19. So what I'm doing here is, I'm just that portion of the data, I'm just replacing it with this cap. Okay, so df dot tip greater than ub. This is the portion which is the outliers. So what I'm doing here, I'm just equal to cap. If I do this, then now if you do, and so I've already capped it. That means I'm replaced the outlier. So now if you check the data again, SNS, see it's clear with the outliers. There's no outliers at all. You check this and you check this. This was the outliers which was there. And now there are almost no outliers. Okay. So this is the handling of outliers. That's all for today. Okay. We have hypothesis testing, which we'll do next time. So let me take the attendance by that time. And I'll upload this, and this will be your practical then. Understood, right? Okay. Okay, so I just take out the Excel sheet.